The networking opportunities here at CppCon are well above and beyond any other C++ conference that I've ever been to.
Hi, everybody, and welcome to everybody out there on internet land. Today, we want to talk about the upcoming new Concurrency TS version 2 for low latency and lockless synchronization. My name is Michael Wong. I'm joined by my colleagues, Megan Michael and Paul McKinney, and they're going to come up, and it's a special treat because they are actually the inventors of these paradigms. So I learned a lot from them trying to make this into a TS. And you'll see that in this talk, they learn a lot from everyone else in trying to turn these paradigms, which were some of it was probably written in C, to the latest modern C++. So it's a real journey. Thank you for coming. Okay, so the agenda is, some of you guys may know that we actually have a Concurrency TS already. So why do we need a new one? What is this TS2? And what is the implementation status of these things? We're going to talk about hazard pointers, and that's Megan Michael. And he's going to show some of the C++ tricks he had to learn. Or maybe he already know them already, I don't know. And then we're going to talk about RCU. And RCU, as I learned almost 15 years ago, is read, copy, update. And that's from, and he was actually my mentor at IBM for the better part of 15 years. And the thing that he learned, Paul McKinney learned, is that how to turn this from C to true modern C++. And trust me, that is a journey, and none of it was easy. So let's dive into it. So don't we already have a TS1? Oh yes, of course we do. It was made in 2015, produced by the Concurrency Study Group SG1. And it's a separate document, and as a TS, is not part of the ISO C++ standard. Now, the goal, of course, with all TS, most TSs for transactional memory, is to eventually get to the ISO standard. And so N4538 is that TS, and it is available on GitHub. And there was a talk by author.The from Microsoft back then in the 2015 CppCon. And what's in this Concurrency TS are improvements to futures. Now, we already had futures, but we wanted to improve it by adding things like then and when any, when all, and things like that. There was also supposed to be latches and barriers. And there was supposed to be atomic smart pointer, but spelled differently than what we ended up with. So since Concurrency TS1, a lot of these things did make it into the C++ standard. Some of it went to C++ 17, some of it went to C++ 20, and as a result, and normal, you withdraw that TS when it's done. And that just actually happened about 2 months ago, maybe actually about a month ago, actually, okay, at the parent meeting of WG21, okay? That's the parent of C and C++. So it's withdrawn. It's technically really out of the picture. I mean, after all, we pretty much unloaded everything, but not everything. Not everything made it. There were a few things that didn't make it. Now, what about this idea of other things for concurrency? This idea of hazard pointers and read, copy, update. These are, as I learned almost 15 years ago, are extremely powerful, low latency, lock-free, lockless programming models. And we've been talking about it since 2014 with talks at CppCon, 2016 as well. And we always like to, couch it in a kind of a jokey but entertaining paradigm, because these things are really hard to follow if you're not at least having some fun. So we like to think of it as, during that talk, we talk about it as being part of Schrodinger's zoo and part of Werner Heisenberg's advice. Things could disappear on you depending which way you look at them. And when you look at it, it's different. But that was, and then we called it a concurrency toolkit at the time, because we really were imagining this as a toolkit of tools that you could use. Now, that was a long time ago, isn't it? 2014. Remember those good times versus today? 6, 7 years. So what have we been doing? Why did it take so long? Well, it took so long because it is slow. Things do take time to get through C++, especially when there's C++ 17, 20 coming. We had to grow older. All three of us have. We changed companies, changed jobs. Our kids graduated. Along the way, we also learned how to convert from a C to C++ interface. We had to learn new and interesting C++ idioms, and you'll see some of those idioms along the way. And we had to learn some new library conventions. So if you're interested in putting things into a library, I think there was a committee question last night asking, here's the place to learn. This is what it took for us to get things into the library. This is all library. There's no language changes here. And we had to work within a tight schedule. By tight schedule, I mean this. If you're a TS, there's really a really small sliver of time in a 3-year cycle where you can literally get time on the committee. Most of the other time, not surprisingly, is devoted to things that are going to the standard. So TSs might be a sliver of time after the previous ratification. And then the deadline starts looming, and now you just have to now start hitting the things that are going to be standardized. So this is why it takes a long time. So you guys have heard of TS, technical specification, and there are quite a few of them in C++. And the question has always been, should you make a technical specification for your favorite feature X or Y? Now, thank you to Shakespeare. Is it Shakespeare who said this? Actually, it was quite appropriate. I'm actually a member of the esteemed group of direction group members. And we've looked at TS very closely as to their role within the committee. They were initially introduced as a way to try things out, give implementation to try specific things, especially on complicated things. So you can get experience on the interface, on the implementations. Over time, the directions group has come to this opinion that you shouldn't use TS on everything in C++ you're trying, because the process takes almost as long, just a little bit shorter. It's just not worth it unless you really have some learning to do. And indeed, we've actually isolated down to the fact that you shouldn't use TS at all for language things. And that's because with language things, they are deeply connected to almost every other component of the language, like overloading, dispatches. So once you can't really isolate a language change such that you don't have to worry about all these other things. But library things you can. So as much as possible, you can use TS for libraries. We pretty much abandoned languages for TSs. The last one was like modules. And you see how long modules took? Okay. And concepts. You saw how long concepts take? So don't use TSs for languages. Use TSs for things that are mostly self-contained units. Another thing that people tend to do to make things a TS is if they don't quite like something, they'll say, okay, you know what, I'll let it go as a TS, but not as a language. That's called a delaying tactic. There's a political term for that too. I think it's called grandstanding. It just doesn't work because it doesn't simplify the process, okay? So as a directions group, we were tasked with asking some of the questions that should be asked. So this is the long list of questions that we urge every TS now to ask if you want to create a TS. But I'll isolate it down to what the direction group pretty much says. You want to make sure that you have these two specific questions. What are we hoping to learn by going through this TS process? Is it some implementation experience? Is it some interface experience? You're not sure. You're not sure. And what are the explicit exit criteria out of the TS? Is it to nothing? Is it to an IS? What does it take to go to an IS? These are very logical things that we demand that people answer. Now, DG is not a directors group, we're a directions group, so it's non-binding. And in some cases, coming out of the TS might even be a new study group because, we can't decide what to do. So, and by the way, you guys, I'm not totally sure, but I think you guys can email this too, or is it just committee members? But there's that email address called directions@list, and it will come to the 5 of us specifically, okay? So what's in the Concurrency TS2? It's quite a few synchronization primitives for lock-free programming on concurrent data structures. And there's actually a whole bunch lined up to come in, but These two are the first two that's going to come. It's hazard pointers and then RCU. And these are the papers that you can easily find now. So, and in future, we anticipate more things coming. Now, some of these may or may not be part of, well, actually, they are concurrency. Things like data structures for concurrent queues and containers, asymmetric fences, maybe executor even goes in there. And there's a GitHub. You can go and look at the TS now, actually. And ultimately, obviously, we wanted to go to an IS, but will it look like the TS when we get to an IS? That's always a good question, because we are free to either substantially change the form of it or change none of it. And these guys are going to tell you what they would like to change. Now, as the Concurrency TS editor, I am empowered, so much power, to add a brand new clause to the C++ standard. And I will intend to add new clause 33 that will add things that of this nature, a concurrency utility library, and something to talk about safe reclamation. I realize asymmetric fences may not be in this list too, but it'll be there somewhere. So the question that you guys are going to try to help us answer is to learn or not to learn. Have we learned enough? What did we learn? What are the exit criteria? Is there still more to learn? Can we stop learning finally? And what is the implementation status? And did this TS process work for us after 7 years? I'd like to invite Mag and Michael to come up and talk about his experiences.
Thank you, Michael. Hi, everyone. So I'm going to talk about the hazard pointers in TS2 and looking at the roadmap and what we plan to propose for C++ 26 and beyond. So very quickly, hazard pointers is a safe reclamation technique. Hazard pointer is just a pointer that can be used by a single thread to protect an object that it plans to use and access. And then on the other side of it, a thread may remove that object anytime and concurrently with the use by the owner of the hazard pointer. But then before it can delete it or reclaim it, it has to check hazard pointers. That's kind of like in a nutshell the technique. It's very simple protocol, and it's fast and scalable, and it doesn't have any dependence, so it can allow protection that can go indefinitely. So in Concurrency TS2, the hazard pointer interface is composed of the hazard pointers themselves, the objects that are protectable by hazard pointers, and domains that manage the hazard pointers and the objects that are retired to that domain. So it's kind of like giving responsibility to the domain to reclaim the retired objects, the objects that were removed from data structures that potentially may be protected or being under use by the owners of hazard pointers, but then they are retired to the domain to take care of reclaiming them when it is appropriate time. So looking quickly at the interface, you can see that the domains they don't really have member functions other than constructor, destructor. There is some kind of customization possibility that we want to explore in the TS to use a custom allocator. And the intent at the time was to enable async signal safety, but we'll see if we learn something from feedback from the users of the technical specification. There's a free function that gives us a reference to the default domain, so that there's always one global domain that's always there, so the user doesn't need to specify that if they're using the global domain. There's a cleanup function for synchronous reclamation, and users can explicitly say, I want to check every object that was already retired so far, and if they are not protected, I want them to be reclaimed before they return from this function. So that's kind of like, it's a capability for synchronous reclamation. I'm going to talk about that in a bit. The second component is the object-based class. And It simply just has a retire member function. This is the way for the user to communicate to the library and saying, I guarantee that I remove this object. Nobody can get access to it anymore unless they already have access to it. And take care of this object to reclaim it when it is appropriate time, when it is not protected. And finally, this is the hazard pointer interface. There are lots of functions, but it's really the essential one is protect. It takes an atomic source and extract a pointer from it, and in that function, but when it returns from it, it will protect that function, that pointer that it will return. The default constructor constructs an empty hazard pointer that cannot be used, so it's kind of useful for moving into. But then there's a function called make hazard pointer to actually make a usable, like a non-empty hazard pointer that can be used to protect object. And that's the interface for TS2. So looking beyond that, here's a usage example using that kind of like the essential interface. So you have the object foo that is inheriting from the object base, and there is you can have two functions representing the two types of threads. The readers and users who are using hazard pointers to protect objects. So these are very fast and scalable. They can just be called frequently, and it's like the overhead is like in the low nanoseconds. Go ahead, please. I can't hear. So, Paul, if you hear that, can you repeat it to me? Go ahead.
Yeah, for the interface for hazard pointer, why does try protect return a bool? Why not return null? Why does try protect return a bool instead of null?
That's the interface that we went with, but. Yeah, it's basically, it's like try protect is telling it, try to protect this specific pointer based on that specific atomic source. The question was, why doesn't try protect return a null a pointer instead of bool, right? So yeah, I think because we know we're just like checking that specific pointer. So it's kind of like, it's either succeeds or not. It's kind of the T pointer is an in parameter. Okay, yeah, it's not an out parameter. No, but it's actually getting updated. So if the try protect fails, it gets updated. So it is out parameter too, similar to compare exchange. It's like when you have a failed compare exchange, it updates the expected value to like the okay. So it's kind of following that. Okay. So the usage example you can see here, it's constructing a non-empty hazard pointer. It's using it to protect some pointer value taken from the atomic source. And then once you have that, as long as the hazard pointer is alive and unchanged, the pointer PTR is protected. So, and that can go on indefinitely. It doesn't, there's no restriction on the use of hazard pointer. On the update side, all what it needs to do, if it is removing an object, then it retires it. Okay. All right, moving on. So this is kind of a background. So as Michael said, the TS process really took a long time, partly like we lots of committees to go through, and actually we had to freeze the functional content of the TS 4 years ago, and we couldn't help learning in these 4 years, so actually we learned a lot. So hazard pointer is actually in implementation and in heavy use in the Facebook Folly library, and there's a lot we went through since then. I'll go through them. This can take a big talk to talk about all these, but I'll just describe what we learned there. So one is synchronous reclamation. The Concurrency TS global cleanup is a powerful tool, but it's blunt. It's expensive. It's basically guaranteeing the reclamation of everything that could be reclaimed in the domain. So it is not very specific. So you have to collect all the objects. You have to check them against all the hazard pointers. And sometimes all what we need is like really, we have a small subset that we care about. And so so over time, this was a high overhead when let's say we have a concurrent hash map, and every time we want to destruct that, we want to check that we destroyed all the keys and values that can be user defined, and we don't know the dependencies there. So Folly introduced cohort synchronous reclamation. I have a whole talk about that tomorrow. So we'll discuss that then. Another thing is integrated link counting. You can do link counting on top of the TS2 interface, but there are certain limitations there. But integrated link counting is actually quite efficient, and it enabled a lot more that we can do with that. So that's part of what we learned there from Folly implementation. Another thing is arrays. It's kind of a simple optimization. It's kind of typically on today's commodity like machines, it takes about like 4 nanoseconds for the thread local kind of construction of a non-empty hazard pointer. So 2 take its nanoseconds, 12 nanoseconds, and so on. But actually, by using an array optimization, it just takes 4, 5, 6 nanoseconds. So we use that a lot in like concurrent hash map and things like that. Another thing is like there were problems with like spikes in latency, because you can retire one object and then end up being stuck with reclaiming like 30,000 objects. And people say, I just, dequeued something from a queue, and now I have like this multi-microsecond delay that I didn't expect. So we made it by default to have a dedicated thread pool, which right now is just one thread. It's totally enough for like tens of thousands of retired objects for doing asynchronous reclamation. And for the rare cases where certain services cannot afford to have extra threads, they can opt out of that. The domains, we also, initially from TS2, we thought that we will use custom domains a lot. And what happened in Folly is actually whenever we had something that looked like it would require a custom domain, we end up finding a way to expand the default domain and make it more robust without losing performance. So it became kind of just like better and better default domain, and we never had to do customization of domains. So we'll see what we learn from the TS experience from other feedback, whether we need to do that or not. Okay, moving from any questions so far about this part. Okay. So next I'm going to talk about like we're thinking, so there's a lot of delay, and if we really waited for the TS2 to take like another 2-3 years to get feedback, we'll be looking at C++29 and beyond. So we want to propose a minimal subset for C++26, and the idea is to like do some, like it's a useful subset that supports asynchronous reclamation. It's compatible with external link counting and automatic retirement, but it's a strict subset. So there's very little work in the committee to go through. We're not going to do custom domains because we don't have any evidence that it's actually needed for the time being. Synchronous reclamation, we're going to rework that. But it should be extensible so we don't paint ourselves in a corner. So we're going to do away with domains for now. For the object base, we'll keep it as is except for the domain part. And also for the hazard pointer, it's like the same as in the TS, except for the domain part. And that's what would look like for C++26. Now, looking beyond that, I mean, that's what we hope to propose for 26. Looking beyond that is that array optimization, it's simple and it's been useful, and it's kind of almost a no-brainer. So that's like extremely likely that we'll propose that beyond 26. Synchronous reclamation There's the cohort technique that I'm going to talk about tomorrow is actually in heavy use, has been very stable. It's actually, we migrated almost completely from the global cleanup to cohorts, and only the global cleanup is left for like testing and benchmarking, which are, nothing like really the functional part. So that's almost that's almost sure to be something that we want to propose. Whether we do that global cleanup or not, it's kind of a more powerful tool. Maybe someone feedback from TS2 will get us there that we need to include that. Integrated link counting is actually quite useful, but I expect that the formal wording will not be simple, so that might take time in the committee. Domains, do we need custom domains? We'll find out from the feedback for the TS. We got feedback from WiredTiger, from MongoDB, that actually they use hazard pointer in a way that they don't give the object to get reclaimed, but they need to check whether it's reclaimable or not, and then they do their own reclamation. So that's something we can add. And as I said, the follow experience has been the default domain can be made very robust. Do we need custom domains or not? Go ahead.
Hi, I was wondering in Folly, what data structures are you using hazard pointers with mostly? Like, what is the biggest use case for this?
Okay, the question is, in Folly, what kind of data structures we use hazard pointer for? There are lots of uses, but there are kind of primary uses are unbounded queue, concurrent hash map, request context, so a lot of like stats that, a lot of model that's similar to what I show is where you have an object, you switch it, replace it with another version that infrequently, and then there are users who are kind of keep reading that. So there are kind of like a long tail of that, but these are the main ones. Go ahead.
So if the array thing is useful, why not just propose that for 23 while you're in there? If the array thing is useful, why not just propose it for 23 while you're there?
If you find something, the question is, if you find something useful, why not propose it for like 23 or 26? It takes time to get the wording right. It's actually, there was a lot of work on that. So that's kind of like we want to give the committee like enough time. They are over, they have a lot of work to go through. So that's the main.
Sorry, I meant 26, not 23.
Oh, right. 26, definitely. Even 26, it's kind of, it takes time.
I would suggest
All right.
if the array is really an essential thing, you should propose it in 26. If the array is an essential thing, propose it for 26.
Right. The question is like, the essential thing is for 26 because it's useful and minimalist. And beyond that, we can more useful and build on top of that. Yes. Okay. Thank you very much. Paul will continue.
I have one more question. Yeah.
Please go.
This was intriguing. You mentioned a case where you would have one hazard pointer that was released, and then you have to clean up 30,000 things. Can you go into a little bit of detail about that?
Oh, right. The question was like, I should describe why I mentioned like 30,000 objects. It's just like asynchronous reclamation is expensive, and so it's amortized. So let's say I'm in a system with like 2,000 threads, and each thread has like 10 hazard pointers. So now we have 20,000 hazard pointers. And then the trigger for asynchronous reclamation is like, let's say we accumulated 40,000 objects, because we want to make sure that we have enough objects that they will definitely find at least 20,000 objects that are not protected. So that's how we amortize it. So it's very amortized, it's expensive. And now we're saying cleanup, and now we're collecting all these objects from all over the place. They might be in private thread local caches, and that's what makes it expensive. Yep. Right.
Wait, so why are you waiting for like 20,000 objects to be reclaimable before you actually do this? What's the expensive part of that?
Why wait for 40,000 objects. Yeah, because that process is expensive. It's like I'm going through 20,000 hazard pointers. So I want to amortize it. I want to make the cost per object like constant.
But what part of that is expensive? Because if you're iterating through 20,000.
Right, that's the regular asynchronous reclamation. That's why it is amortized and efficient. But now someone says cleanup. Now they have to pay that cost for potentially a very small number of objects because they are saying cleanup now.
It might help if you do it too quickly, you get to scan ones that are still in use repeatedly.
I didn't hear you, but okay. I'll let Paul continue, and then maybe we can take more questions at the end. Thank you.
Thank you. Thank you, Megan. So I want to, before I start, answer one of Michael Wong's questions. I want to also thank my co-presenters. He said, when do we stop learning? We stop learning shortly after our funerals. It does. It's just, yeah, he said it doesn't stop. I'm contradicting him. Anyway, so Megan covered hazard pointers. I'm covering RCU. There are some similar sorts of things. We do batch reclamation, for example, in both. I actually had my first C++ standards committee meeting in 1990, and my second one in 2007. And my only C++ project, paid for work, was in 1990. And that meant that my initial attempts at writing bindings, a library for RCU, used this keyword virtual that you might have heard of. And they were building abstract classes. This resulted in some pointed feedback of the form, where'd you get that code from anyway? A museum? Why, yes, I did. So, yeah, I had to learn a lot to get from 1990 to the 2000s pretty quickly. And what I used, and this is apparently is common practice, is something I call diagnostic-driven development. And what you do is you look at CPP reference, you look at other code, and then you try typing something in that looks like it might sort of do what you want, and you get a whole pile of compiler diagnostics. And so you look at the diagnostics and use that as additional information to modify your code to try to get something. And I got backed into a corner. I was trying to use this template stuff and this derived types and everything, and no matter what I did, I was getting diagnostics in one form or another, and my only way out was that thing. And I mean, I'm defining a class, a struct actually in this case, and I'm passing it to my base class I'm deriving from before I've defined the class. And how's that supposed to work, right? Well, but I didn't have any other alternatives, so I typed it in. And it compiled. And then I ran it, and it did what I wanted. So like many others before me, I had a trial by fire in the magic of CRTP, the curiously recurring template pattern. And apparently, in the initial appearance of it back decades ago was a surprise to the people who were working with it. So I guess I'm following in good footsteps. Okay, so this was one example. Given my Cold War child status, I'll call it mutually assured education. The problem we had was that my knowledge of C++ was very limited and very old. And it's still kind of limited, rather really limited actually. And everybody else's knowledge of RCU was similarly limited. And the problem I had, and I've been having this in multiple areas, so I'm finally getting around to trying to address it separately, not in this talk, is that people will find one use case and glom onto that and think that's all there is. And then they'll try to get me to do an RCU thing that just does that, which is fine for that. And so it took a lot of back and forth to make that work. We have a reference implementation, and that's a GitHub address for it, and the directory for the current one is there. And I really want to thank especially three guys, Arthur O'Dwyer, Dwayne Holman, and Izzy Murite. These are the guys that taught me by giving me code. And that was really, really helpful. We had to do things a little bit differently, but it really helped me understand what the heck I was even trying to do, what the landscape was. There was lots of discussion afterwards, and there's a whole bunch of people, including, of course, my co-presenters, who I need to thank, but there's way more than are going to fit on a slide, and their names are immortalized in a whole pile of working papers and also in a bunch of discussion notes. So thank you, everybody, for getting me up to speed on this. It was not an easy thing. I'll be talking a little later about how it wasn't easy in certain circumstances. There was a little bite shedding along the way. For example, we use template of T instead of abstract and virtual and all that. We had this thing called synchronized RCU, which is the way it is in the Linux kernel and probably always will be, but having RCU underbar synchronized is consistent with all the other free functions, which start with RCU underbar. One that was kind of hard fought was the RAII thing. I had, initially I just had a free function you call to say start a reader and another one to call to stop a reader, which is the way it is most other places. But got talked into RAII, so I made a class that did RAII RCU reader and eventually got talked into an RCU domain, which is CPP17 basic lockable. And we'll talk more about how this is and why it was so hard to get me to do that, okay? This was not, I fought this every step of the way, all right? And I had reason to. But we do have an RCU domain as a result, so I'm kind of going in the opposite direction of hazard pointers. The reason is they don't have scope readers. They just work on a per object basis, hazard pointers do. RCU needs to delimit code, and therefore RAII comes into play. Right now, there's only one of them, and we'll talk more about that later as well. Mag had talked about having deleters invoked immediately from the retire call in RCU. In hazard pointers, the same effect can happen in RCU for the same reasons. The work of determining when all the readers is done is expensive, or it can be. And we don't want to do that very often, which means that once we do, there may be a very large amount of deleters, very large number of deleters waiting to be invoked. And we need to be able to have some control over that. Now, initially, it's not a big deal because almost always they're free memory, okay? So right now, we're saying, yes, they can be invoked from a retire call. We'll talk more about that later. Non-intrusive was a difficult one. In the Linux kernel, we make everything's intrusive. And the reason is you never in the kernel, almost never, want to allocate memory on the free path. Because that's an excellent way to end up with out-of-memory deadlocks. Because you're trying to free this memory, but you need to allocate memory before you can free it, and you can't allocate the memory because you haven't freed the memory that you're trying to allocate the memory in order to free. And that's something you try really hard to avoid. The difference, the reason why we have a non-intrusive RCU retire is because in C++, it's a different world than Linux kernel, and it's not unusual for if you run out of memory, just kill the application and restart it. People usually get a little upset if you require them to do that to their kernel very often, but life is different in applications for at least some applications. And in addition, we actually have a non-intrusive RCU retire in the Linux kernel, named differently. The difference there is that we avoid the out-of-memory deadlock by synchronously waiting for a grace period. If we're out of memory, say, okay, fine, wait for all the readers to get done, and then we'll let it go. So we can not allocate any memory and still make forward progress, even non-intrusively. Expensively in terms of latency, but that's the user's lookout. Okay, what are this RAII readers? I'm going to go through this in a little bit of detail because I think it might be useful when talking to other people coming from C backgrounds or other backgrounds not having destructors as to why I was having so much trouble with this. So this is something that we can do right now. You've got a reader. It does something before the reader starts. Then we make a unique lock. We give it the STD domain type. We give it a name of the variable, in this case, RDRU. And then we give it the default domain. And that tells it, okay, great, enter in a reader and set it up so when that variable goes out of scope, we exit the reader. And so when we hit that curly brace, we leave the reader. And so we can do something within the RCU reader while that's happening. And this could be happening concurrently on a whole pile of threads all at once. That top function might be called by a whole bunch of people all at once. The updater, as people familiar with RCU would expect, we do a RCU synchronize, and that waits not for all readers. This is not a reader-writer lock, but for all pre-existing readers. If the reader got there first, it might be seeing an update. It might be seeing some stuff that was removed. We need to wait for that reader. If the reader started later, that reader has to see the fact that things were removed. It can't have a reference to the removed thing, so it's okay not to wait for it. All right? So we have a kind of a weak wait for pre-existing readers, and we have this RAII thing, so we can let close curly brace do its magic for us. And that means multiple readers at the same time can see conflicting results. The cat can be both dead and alive. This is reality. Speed of light means that the outside world you're tracking takes time to get in memory. Your pristine memory state is out of date anyway. And so having different readers have different ideas actually works, not always, but in a great number of situations. And we have ways of making RCU be consistent if you need it to be. Okay. Now the problem is that not all the world can live within the confines of an RCU RAII reader, and in the Linux kernel it's actually kind of rare for that to happen, which is why I fought so hard against the concept. Now what we can do, and this is something that was education, you can use the RAII functions, but you can use STD-move to kind of move a token representing that reader. So we can return that token from this function. So we can make the start deferred reader just be the start of a reader. And then we can call this guy at the end, STD moving the token back in, and that closed curly brace will get out of the reader. And that allows us to put the beginning and the end of the reader wherever we want, regardless of any scoping. Okay? And if you can use RAII, of course you'll want to, but we'll see where it's, but we'll start with a simpler example first. This is gonna be a stupid example, but it's a simple one. This is whenever the spirit STD moves you, is how this works. So you do something before the reader, you enter that reader, that's a function on the previous page, you STD move the return value, so the lifetime doesn't end, and you're still in the reader. Then you do something within the reader, okay, call some function, and then we do this end deferred reader, which is just an empty function. We STD move the local variable back into the parameter, and then that parameter's lifetime ends before the function returns, and that means we exit the reader. So the reader begins at that auto RDR function and it ends at the end deferred reader function, and we have complete control of exactly where it is. Of course, this is stupid. I mean, why not just have an extra pair of curly braces and give yourself a scope, right? Okay, but that was a simple case. If we do something a little more complicated, and this is a real common use case for RCU, we have some linked data structure we're searching. And we use RCU to protect the traversal of that data structure. Once we hit the object that we're searching for, we acquire a lock on that object. So we've got this dotted circle with RCU controlling all the links between these things. Okay, controlling traversal of the data structure. Once we get to the object we're looking for at the leaf, we acquire a lock or a mutex or what have you inside that object. And that means that we can have guys concurrently going down this tree. There's only one route, but it doesn't matter. The readers go charging through that route without any kind of locking or anything. Very fast, very scalable. And then only when we get to the bottom where we need the mutual exclusion do we do it. If we've got a big tree, we have a huge number of locks, we can get a huge amount of concurrency, and it works very well. This is a very typical use case. And that means we need something like this. We want to update the object, all right? So we start the reader, just like we did before. And the comment is what you do in the Linux kernel, just because I have a hard time remembering from these funny names. We find the object. That's some function that goes and traverses the tree and gives us the object. And we get a pointer to it. And we locklessly check to see if it needs update. Now it's kind of like double-checked lock in a funny way. We check to say, do we need an update? If we don't need an update, let's not mess with the lock, let's not take the contention. Let's just go down to the else clause and end the reader and get on with life. We looked it up, it doesn't need to be updated, let's go. If it does need to be updated, we do lock guard on a mutex in that object. We can acquire that lock safely because RCU is preventing that object from going away. It can't be freed. Once we get the lock, we can get out of the RCU reset critical function. We hold the lock now, and the lock prevents the object from going away. All right? And then we check again if we need update, this time holding the lock, so we've got a guaranteed situation. And if we need an update, we do an RCU unsafe locked update. That's why we have to be outside the reader. It's doing something that you can't do inside a reader, like RCU synchronize. And then the closed curly brace before that else gets us out of the lock. And we can't possibly make this fit. Well, let's take a look at the scope of things. So instead of the tree like we had a couple slides ago, we're going to draw the boxes around the code this time. So the RCU protection is from the reader's start to the reader's end and the else clause. Okay, so that's the protection in the code of the RCU reader. And the lock protects that stuff. And there's some overlap. There's a period of time when both RCU and the lock are protecting things. And then we get out of RCU, and then we can do this stuff that RCU readers can't do, but needs a lock to protect it. And there's no way you can make a nesting do that. You can't use RAII for this situation. Does that make sense? Sort of. But anyway, this example is why it was so hard to get me to think about RAII for RC readers, because in Linux kernel, it never works, all right? But, you know, C++ applications aren't the Linux kernel. This is similar to Magid's thing about retire and deleters. I asked about it, and I got some feedback from the QME developers who use a user space RCU in C, and they don't like that because it induces deadlocks. And here's how that can happen. You got somebody who's going to invoke retire. They get a guard on some global mutex. They do a retire. That retire invokes a whole pile of deleters. They just happen to show up at that time. Other deleters, unrelated to this retire. And one of those, if it's going to acquire a mutex, that my mutex, the same one, we got deadlock. Game over. All right? So that's the complaint the QME guys had. They just hit this all the time. But there are environments where you can't just create threads willy-nilly, and they need something. One approach is to do what Magid suggested. I like that approach. I like having the caller give the threads in. Another one is to have a static function that if it returns false, deleters from retire. If it says false, then the implementation is promising you there will be no deleters invoked from retire, therefore there can be no deadlocks like that. And there's a bunch of other options you could take as well, which I won't go through in detail. Here are some other questions we might have. There are some lock guards where you have to specify the RCU type and the default domain. Maybe some additional constructors would help avoid that. There are some users who want a rough count of the outstanding deleters so they can restrain themselves if there's a whole pile piling up, for example. We might need multiple instances of RCU domain. That's later. We have that in the Linux kernel, but it was years before it showed up. And of course, memory order consume has been a thorn in my side, and yours probably as well for a long time. You can still use it. It just promotes to require. It works just fine. None of these, however, is on the critical path to IS. I would consider these to be TS learning that might feed into later. I would hope to get a basic thing into 26 and maybe this stuff hammered out for 29 or later. Anyway, that's where we are. Final words, I guess. We have TS2 on GitHub right now. You can clone it, run LaTeX on it, produce it, make a PDF. That's where it is. And that means we have two of them actually there right now. The old one's still there, even though it's been withdrawn, and the new one is up now. And here's again what we've got. Michael went through the various things in making the standard work. He's been my mentor forever for making that happen. And also going through hazard pointers with Magid and RCU with myself. So at this point, if questions, we can take them. Suggestions, thoughts, things you'd like to see, or warnings of impending doom if we follow this path. And of course, the thing, if you're gonna do the impending doom before following the path, you need to also tell us, ensure us there's worse doom on all the other paths, right? We want the least doomy path. Go ahead.
Instead of still moving the lock guard to the end deferred reader, can you just assign it to the empty lock guard?
If instead of STD moving it, can you just assign it? I tried that and bad things happened, maybe because I was doing something stupid. But if we can get in touch later, I've got the code and we could try, you can tell me to try different things and we can see what happens. So you're suggesting instead of STD move, I just assign it. Yeah. I think what happens is he yells at me and tells me I don't have a copy constructor.
Okay.
But, okay, and somebody knows a lot more about C++ in the back is nodding his head yes, so I'll say I dodged that bullet. Good question, though. I tried it. Other questions? For Magid, go ahead. Notable open source implementations. I've got the one on GitHub. I've got a wrapper around the C language user space RCU. And it just takes the C things and maps them in there. So that's there. I've not been as industrious as Magid. I have not yet converted the Folly library to use this, but that's something I promise to get started on. I promise management I get started on real soon now. But yeah, I was, life, you know, life is what happens while you're making other plans. Good question though. Yes?
So question from online. My understanding, extremely poor, of RCU is that it works in the kernel because you don't get interrupted. How does that work in user space?
Okay. So there are multiple flavors of RCU, and that description is accurate for some of them. The key point is that you have to have some way of deciding that you're not in a reader. And you have to decide that nobody's in a reader, and then you can say, great, we can clean people up. So in the C++ implementation I have now, when you do RCU unlock, it says I'm no longer a reader using one of a number of methods depending on how you built your user space library. And what the real requirement is, not that you don't have interrupts or that you go through a scheduler or do something, the real requirement is you never spend forever in a reader, which is similar to never holding a lock forever, right? Never holding a reference forever, and similar things like that. So you do have to have some discipline, but it's not like you have to, it's not, so let me say it a different way. The things about having scheduling points happening fairly often, or idle, or any of a number of other things in the kernel are heuristics and optimizations the kernel uses to very efficiently compute RCU grace periods, okay? And in user space RCU and in the C++ wrappers for it, we don't have to do it that way because we're not the kernel. So we make use of other mechanisms that get the same effect. Did that help? Go ahead.
Like it is kind of like then are you never like considering the application of like such a data structure in bare metal environment, like such a I'm building a kernel myself, say, and like is it like with the current assumptions, do you think it's like unreasonable to use the standard version? Like will I have to still build my own, or can I just like fully?
Okay, let me see if I got the question right. So it sounds like what you're asking is, you know, we've got this standard thing we're doing, it's got user space RCU, but suppose I'm in a deep embedded microcontroller and I want to use RCU. Is it really going to work for me? Okay, and we have user space RCU might or might not work in a deep embedded microcontroller, but we do have implementations of RCU we've had in the past that are very heavily optimized for being small and being efficient. For example, the old versions of Linux kernel RCU used, let me back up and say something different. For example, you might not want the extra threads, okay? Well, what you could do in your implementation, you're saying I want to implement this myself maybe, or you're wanting to have an embedded library that works for that class really, really well for that class. And you're saying, you know, I don't trust glibc and I'm not going to trust your glibc RCU either, which is not unreasonable if you're working in that specialized environment, to be honest, right? In that case, you might use RCU barrier to drive the process. And the reason for that is that unlike retire, RCU barrier already has all the latency consequences and already has the restrictions about don't deadlock yourself. And so you could choose something like that to make it work with almost no extra stuff. But if you're specialized enough, you're going to have a specialized implementation. Other questions? Well, if there are no more, I very much appreciate your time and attention. Hopefully this helped understand how you can better talk to C guys like Maggot and myself. There may be other languages that have similar interesting views. And hopefully this helps give you some views into what it takes to set up a concurrency TS, or a TS in general, and when you want to use one or not. Thank you all very much.